What if the building blocks of life didn't just appear, but emerged from cosmic chaos in ways we're only beginning to understand? Picture the universe in its earliest moments, a swirling sea of particles too hot and violent to form anything stable. Yet somehow, against all odds, the first complex molecules took shape, setting the stage for everything that followed. These molecules weren't just random accidents. They were the universe's first whispers of chemistry, the hidden architects of life itself. And here's the astonishing part: scientists still don't fully agree on how they got there. Some theories sound like science fiction, others like pure poetry, but each one offers a glimpse into the cosmic puzzle that made our existence possible. The story of these molecules isn't just about atoms bonding. It's a saga of survival against impossible odds. Imagine a young universe, barely a few 100 million years old, where temperatures could vaporize rock and radiation tore through space like a storm. In that hostile environment, how did delicate structures like water or even simple organic compounds hold together? The answers might rewrite everything we know about chemistry's origins. From lightning strikes in primordial clouds to the gentle dance of dust grains in deep space, researchers have proposed at least 30 wildly different explanations for how complexity arose from chaos. Some ideas point to the hearts of dying stars, while others suggest molecules could have formed on the icy surfaces of asteroids, carried across the cosmos like celestial seeds. This isn't just about distant history, it's about unlocking the secrets of life's blueprint. Every living thing on Earth, from the tallest tree to the tiniest microbe, owes its existence to those first fragile molecules. And if we can piece together how they formed, we might finally answer the ultimate question. Are we alone in the universe? The clues are out there, hidden in the light of ancient galaxies, the chemistry of distant planets, and even the rocks beneath our feet. So let's dive into these 30 theories, each one a thread in the grand tapestry of cosmic origins. Some will surprise you, others might challenge what you thought you knew, but together, they'll take us closer to understanding the universe's greatest magic trick, how nothing became something and something became us. One of the most enduring ideas about life's origins starts with a simple image: Earth's ancient oceans simmering like a cosmic kitchen where the first ingredients of life came together. This is the primordial soup hypothesis, a theory suggesting that our planet's early waters were filled with simple chemicals like ammonia, methane, and hydrogen, swirling in a broth just waiting for the right spark. Picture towering volcanic vents spewing heat, lightning cracking across stormy skies, and ultraviolet rays from a young sun piercing through a thin atmosphere. These violent forces didn't just create chaos, they might have been the very tools that stitched atoms into the first complex molecules. The groundbreaking Miller-Urey experiment in 1953 brought this idea to life in a lab. Scientists Stanley Miller and Harold Urey recreated Earth's early conditions by sealing water, methane, ammonia, and hydrogen in glass flasks, then zapping the mixture with electric sparks to mimic lightning. Within days, something astonishing happened. Amino acids began to form the same building blocks found in every living cell today. It was as if they'd watched the universe's recipe for life unfold in real time. This experiment didn't just support the primordial soup idea. It showed that complex molecules could arise from simple ingredients under the right conditions. But here's where the story gets even more fascinating. While the Miller-Urey experiment became iconic, later research revealed that Earth's early atmosphere might not have matched their exact setup. Some scientists argue there was more carbon dioxide and nitrogen, less methane and ammonia. Yet, even with these tweaks, similar experiments still produced organic molecules, just through different chemical pathways. This adaptability suggests the primordial soup wasn't a single recipe, but a whole cookbook of possibilities. Critics point out that amino acids alone don't make life. They need to link into proteins, and those proteins need to replicate. But the soup hypothesis doesn't claim to solve every mystery, just the first step. Think of it as the universe's way of setting the table. The real magic might have happened when these molecules found their way to hydrothermal vents or clay surfaces, where minerals could act like molecular scaffolds, guiding simple compounds toward greater complexity. What keeps this theory alive after decades isn't just nostalgia, it's the sheer elegance of its simplicity. The idea that life's ingredients could simmer in Earth's early waters, stirred by natural energy sources, feels almost inevitable. And while newer theories explore spaceborne molecules or deep-sea vents, the primordial soup remains a cornerstone. It reminds us that sometimes the most profound discoveries begin not in the void of space, but in the quiet chaos of a simmering pot, waiting for the right moment to bubble over into something extraordinary. Deep beneath the waves of Earth's ancient oceans, where sunlight never reaches and pressure crushes like a vice, another cradle of chemistry might have been at work: hydrothermal vents. These underwater geysers, spewing superheated water rich in minerals from the planet's crust, could have been the universe's first laboratories. Unlike the chaotic surface storms of the primordial soup, vents offer something extraordinary: stability. Picture a column of mineral-rich water heated by Earth's magma, rushing upward through porous rock. As it rises, the temperature drops sharply, creating a gradient, a natural staircase of energy where molecules could climb toward complexity. The real magic lies in the vent structure. Their rocky surfaces are pocked with microscopic nooks and crannies, each one acting like a tiny test tube. Minerals like iron and sulfur, abundant in these environments, don't just sit there, they actively participate in chemistry. Imagine them as cosmic matchmakers, grabbing passing atoms and nudging them together. In lab experiments, scientists have watched simple molecules like carbon dioxide and hydrogen cling to these mineral surfaces, reacting to form more complex compounds. Some vents even contain microscopic pores that mimic the shape of cellular membranes, hinting at how life's first boundaries might have formed. Recent discoveries have added fuel to this theory. Near modern vents, researchers have found not just simple organic molecules, but entire chains of amino acids and even lipids, the same stuff that makes up cell walls. Even more striking, some vents host what scientists call chemical gardens, eerie, chimney-like structures that grow where hot vent fluid meets cold seawater. These gardens aren't just geological oddities, they're dynamic reactors, constantly cycling chemicals and energy in ways that could have jump-started molecular complexity. Critics once argued that vent environments were too harsh for delicate organic molecules, but nature keeps surprising us. Certain vents, known as alkaline hydrothermal vents, have a gentler chemistry. Instead of scorching acidity, they produce warm, alkaline fluids rich in hydrogen, a perfect recipe for the kind of reactions that build rather than break. It's like comparing a volcano to a slow cooker. Both provide heat, but one gives molecules the time and conditions they need to assemble into something greater. What makes this theory so compelling is how it bridges chemistry and biology. Vents don't just supply ingredients, they offer an entire system. Energy gradients to power reactions, mineral scaffolds to guide assembly, and protected microenvironments where fragile molecules could survive. It's as if the Earth itself knew the recipe for life and cooked it low and slow in the depths. And if this happened here, why not on ocean worlds like Europa or Enceladus? The vents we see today might be faint echoes of those ancient crucibles, but they're a reminder that life's origins could be hiding in plain sight, not in the void above, but in the simmering dark below. Now imagine if the seeds of life didn't even originate on Earth, but hitched a ride across the cosmos on celestial taxis like comets and meteorites. This is Panspermia, the idea that the universe's first complex molecules weren't forged here but delivered, like a cosmic care package from the depths of space. The evidence comes from some of the oldest travelers in our solar system, meteorites. In 1969, a fireball streaked across the sky over Murchison, Australia, scattering fragments that carried something astonishing: amino acids, the same organic building blocks found in every living cell. This wasn't an isolated discovery. Since then, scientists have identified dozens of meteorites packed with organic material, some even containing sugars and nucleobases, the raw ingredients of DNA. But how could delicate molecules survive the brutal journey through space? The answer lies in the protective embrace of asteroids and comets. These space rocks are more than just debris. They're time capsules, shielded from harsh radiation by layers of ice and dust. Some comets, for instance, contain organic, rich ices that act like cosmic freezers, preserving fragile compounds for billions of years. When these objects collide with planets, they don't just bring destruction, they might deliver the very chemistry needed for life to take root. Lab experiments have shown that amino acids can endure the extreme heat and pressure of atmospheric entry, nestling safely inside the fractured remains of their cosmic transports. The implications are staggering. If life's ingredients are common in space, then Earth might not be unique, just lucky. Recent missions like Japan's Hayabusa 2 have added fuel to this theory. When the spacecraft touched down on the asteroid Ryugu in 2019, it collected samples that later revealed a treasure trove of organic molecules, including uracil, a key component of RNA. Even more compelling, the Rosetta mission found the amino acid glycine clinging to Comet 67P, drifting through the solar system like a molecular breadcrumb trail. Critics argue that Panspermia merely shifts the mystery elsewhere. After all, how did those molecules form in space to begin with? But here's the twist: the interstellar medium itself might be a vast chemistry set. In the frigid clouds between stars, dust grains coated in ice become tiny reactors, where ultraviolet light and cosmic rays trigger reactions that build complex organics. Telescopes have detected everything from ethanol to formaldehyde floating in these cosmic nurseries, suggesting the universe is far more chemically inventive than we once thought. What makes Panspermia so captivating isn't just the science, it's the sheer audacity of the idea. Life's beginnings might not be tied to a single planet, but woven into the fabric of the cosmos itself. Every time a comet streaks across the sky or a meteorite crashes into the desert, we could be witnessing the same delivery service that, billions of years ago, brought the first whispers of chemistry to our newborn world. And if that's true, the search for life's origins isn't just digging into Earth's past, it's reaching for the stars. Sometimes the most profound discoveries don't come from high-tech labs, but from the ground beneath our feet, literally. Enter the clay catalyst theory, an idea so elegantly simple it feels almost inevitable. Picture Earth's early landscapes, vast stretches of wet clay baking under a young sun. These unassuming minerals, often overlooked, might have been the universe's first molecular workshops. Unlike the violent chaos of lightning storms or the crushing depths of hydrothermal vents, clay offers something different: order. Its microscopic layers are stacked like pages in a book, each one a potential template for chemistry. The magic lies in clay's unique structure. Those tiny layers are negatively charged, acting like molecular Velcro for positively charged molecules floating in water. Imagine amino acids or nucleotides, the building blocks of RNA, drifting into these narrow gaps. Suddenly, they're not just floating freely, they're lined up, held in place close enough to react. It's as if the clay handed them a blueprint for assembly. Experiments have shown astonishing results. When RNA components are mixed with certain clays, they spontaneously link into chains, sometimes reaching lengths comparable to those found in living cells. Some clays even accelerate these reactions by a factor of 100, acting as ancient catalysts long before enzymes existed. But clay didn't just assemble molecules, it protected them. In a world bombarded by ultraviolet light and battered by tidal forces, delicate organic compounds needed shelter. clay's layers provided a safe haven, shielding fragile chains from destruction while giving them time to grow more complex. Researchers have recreated these conditions in labs, watching as montmorillonite clay, a common type found in volcanic ash, helps form not just RNA-like strands, but also vesicles resembling primitive cell membranes. It's as if the Earth itself provided a toolkit with clay as the multipurpose tool. The theory gains even more traction when you consider clay's ability to concentrate molecules. In watery environments, dilute ingredients rarely react, but clay acts like a sponge, soaking up organic material from surrounding water and packing it into dense pockets. This concentration effect turns a quiet pond into a bustling molecular marketplace, dramatically increasing the odds of meaningful collisions. Some scientists compare it to a prehistoric version of modern lab equipment, a centrifuge and test tube rolled into one. What's truly remarkable is how this idea bridges geology and biology. Clay isn't alive, yet it exhibits lifelike behaviors, selecting certain molecules, organizing them, even growing and replicating its own layered structure. This blurring of boundaries hints at a deeper truth, that the line between non-life and life might not be a sudden leap, but a gradual climb, with minerals like clay providing the footholds. And if this process happened here, could it be happening right now on Mars, where clay deposits abound? The red planet's ancient riverbeds might hold more than just water stains. They could preserve the very scaffolds that once cradled the universe's first experiments in chemistry. Freezing temperatures might seem like the last place you'd expect chemistry to thrive, but space has a way of turning our assumptions upside down. Far from being a barrier, ice could have been the universe's secret weapon for forging life's first complex molecules. Picture the vast, cold stretches between stars where temperatures plunge hundreds of degrees below zero. In these frigid voids, dust grains become coated in layers of ice, not just water ice, but frozen methane, ammonia, and carbon monoxide too. These icy mantles act like cosmic petri dishes where simple molecules huddle together, shielded from destructive radiation. And here's the twist: when bathed in the faint glow of starlight or zapped by cosmic rays, these frozen mixtures don't stay simple. They transform. Lab experiments have revealed something astonishing. When scientists recreate these icy conditions and simulate space radiation, the ice doesn't just sit there, it becomes a factory for organic molecules. Take glycine, the simplest amino acid. In one experiment, researchers froze a mix of water, methanol, and ammonia, then bombarded it with ultraviolet light. Within days, glycine appeared, as if the ice itself had orchestrated the reaction. Other studies have produced even more complex molecules like ribose, a sugar critical for RNA. The cold isn't just preserving these compounds, it's actively helping them form. How? Ice's crystalline structure forces molecules into tight, orderly arrangements, increasing the chances they'll collide and react. It's like a molecular slow dance where the cold tempo gives chemistry the precision it needs to build rather than break. The interstellar ice hypothesis gains even more weight when we look at real cosmic environments. Telescopes have detected organic molecules in frigid molecular clouds, the same nurseries where stars and planets are born. Some of these clouds contain formaldehyde, hydrogen cyanide, and even ethanol, all trapped in icy grains. When these grains drift into warmer regions, like the disk of a forming solar system, the ice sublimates, releasing its molecular cargo onto asteroids or fledgling planets. This could explain how Earth inherited its chemical starter kit, not just through random chance, but as part of a universal process playing out across the galaxy. What makes this theory so compelling is its universality. Unlike Earth-bound scenarios which depend on local conditions like volcanic vents or lightning storms, icy chemistry could happen anywhere, on a moon of Saturn, in the heart of a distant nebula, or even on a comet halfway across the galaxy. Ice doesn't discriminate. It's a democratic medium offering the same chemical opportunities to every corner of the cosmos. And if that's true, the building blocks of life might be more common than we ever imagined, waiting patiently in the freezer of space until the universe decides it's time to thaw. Volcanoes don't just reshape landscapes, they might have rewritten the very rules of chemistry in Earth's early atmosphere. Picture a planet still cooling from its violent birth, its skies choked with volcanic gases like methane, ammonia, and carbon dioxide. These weren't just emissions, they were raw ingredients swirling in a planetary-scale reactor where heat, pressure, and lightning turned simple molecules into something far more complex. The key lies in the unique conditions of volcanic plumes, columns of gas and ash so turbulent they generate their own weather. Within these towering infernos, static electricity builds until it erupts in jagged bolts of volcanic lightning, a force potent enough to crack molecules apart and rearrange them like cosmic Lego bricks. Lab experiments have shown just how transformative these reactions could be. When scientists simulate ancient volcanic atmospheres mixing gases like nitrogen and methane with sparks to mimic lightning, they observe something remarkable: amino acids forming within minutes. It's not just the energy of the lightning that matters, but the cocktail of gases themselves. Volcanic emissions often contain hydrogen sulfide and cyanide, compounds deadly to modern life but potentially vital for kickstarting probiotic chemistry. These molecules act like chemical middlemen, bridging reactions that would otherwise never occur. One study even found that volcanic lightning could produce nucleobases, the letters of the genetic alphabet, suggesting volcanoes didn't just contribute to life's building blocks, they might have helped spell its first words. But the real breakthrough came when researchers looked beyond the lab. In 2016, sensors near Alaska's Bogoslov volcano detected organic molecules in its plume, actual proof that volcanic eruptions can synthesize complexity in the wild. Even more compelling, analysis of ancient rocks reveals traces of organic carbon in layers formed during periods of intense volcanic activity. It's as if the Earth left us a chemical paper trail, with each eruption adding another piece to the puzzle. What sets this theory apart is its scalability. Unlike localized environments like hydrothermal vents, volcanic gases could have blanketed the entire planet, turning the sky into a global laboratory. And it wasn't just Earth's volcanoes doing the work. Some astrobiologists speculate that Io, Jupiter's hyperactive volcanic moon, or even ancient Martian volcanoes might have created similar conditions elsewhere in the solar system. The implications are staggering. If this process happened here, it could be a universal phenomenon, with fiery mountains acting as silent alchemists across the cosmos. Yet the most poetic detail might be the role of ash. Volcanic plumes don't just disperse, they settle, dusting land and sea with mineral-rich particles. These tiny fragments could have carried newly formed organics to Earth's surface, seeding environments where the next steps toward life could unfold. It's a reminder that destruction and creation are two sides of the same coin, and that the same forces that once scarred our planet might have also given it the gift of chemistry's greatest masterpiece. Lightning doesn't just illuminate the sky, it might have been the spark that ignited life's chemical origins. Picture Earth's early atmosphere, thick with water vapor, methane, and ammonia, crackling with the energy of countless lightning storms. Each bolt carried enough power to rip molecules apart and reassemble them into something new, like a celestial blacksmith forging the first links in life's chain. This idea isn't just speculation. Modern labs have recreated these ancient storms, revealing how a split-second burst of electricity could have set the stage for complexity. The magic lies in lightning's ability to break and remake chemical bonds. When a bolt tears through the air, it superheats the surrounding gases to temperatures hotter than the sun's surface, but only for a fraction of a second. This intense, fleeting energy creates a shockwave of reactions, transforming simple molecules like methane and nitrogen into cyanide and formaldehyde compounds that might sound toxic to us but are surprisingly versatile building blocks. In the 1950s, Stanley Miller's famous experiment showed this process in action, but recent research has taken it even further. Scientists now use pulsed plasma discharges to simulate lightning more precisely, watching as these controlled bursts generate not just amino acids, but also nucleobases like adenine, a key component of DNA. It's as if the universe encoded a recipe in the very chaos of a storm. What makes these findings even more compelling is how they intersect with other theories. Lightning doesn't work alone. It needs an atmosphere primed with the right gases. Early Earth's volcanic activity and ultraviolet bombardment likely created a reactive cocktail perfect for lightning to work its alchemy. And while Miller's original experiment assumed an atmosphere rich in methane, newer studies show that even with more carbon dioxide and nitrogen gases now thought to dominate Earth's early air, lightning can still produce organic molecules just through different pathways. This adaptability suggests that electric sparks could have been a universal tool, not just for Earth but for any rocky planet with a stormy sky. The real surprise comes when you consider scale. A single lightning bolt might seem insignificant, but over millions of years, Earth could have experienced trillions of them, each one a tiny molecular workshop. Calculations suggest that lightning alone might have produced thousands of tons of organic material annually, raining down into oceans and lakes to form concentrated pools of prebiotic soup. And it's not just terrestrial lightning that matters. Scientists have observed discharges in the ash clouds of erupting volcanoes, a phenomenon that could have supercharged the chemical factory of early Earth. Yet the most tantalizing question isn't just how these molecules formed, but how they survived. Lightning's fury can create, but it can also destroy. The answer might lie in timing and location. Storms over shallow water, for instance, could have deposited newly minted organics into tidal pools, where clay minerals or evaporating edges protected them from further breakdown. This delicate balance creation, followed by preservation, hints at a larger pattern in the universe's dance toward complexity, chaos and order, working in tandem to turn flashes in the dark into the foundations of life. What emerges from these experiments isn't just a theory, but a vivid portrait of resilience. Against a backdrop of boiling oceans and fiery skies, lightning stands as both destroyer and architect, its fleeting brilliance etching the first strokes of chemistry's greatest masterpiece. And if this process unfolded here, why not on distant worlds where storms rage under alien suns? The answer might be written not in stone, but in the electric language of the cosmos itself, a script we're only beginning to decipher. The same sunlight that burns skin today might have been the unsung hero of life's earliest chemistry. While we shield ourselves from ultraviolet radiation, Earth's shallow pools and misty aerosols 4 billion years ago had no such protection, and that could have been their greatest advantage. Picture a world without an ozone layer where UV light streamed in unchecked, striking the surfaces of tidal flats and misty droplets with relentless energy. At first glance, this bombardment seems purely destructive, breaking apart fragile organic molecules faster than they can form, but nature thrives on paradoxes. That destructive force also held a creative secret: the power to stitch simple molecules into complex chains through a process called polymerization. Laboratory experiments reveal UV's surprising duality. When scientists expose mixtures like hydrogen cyanide and water to ultraviolet light, something remarkable happens. Rather than just breaking down, these molecules begin linking together into longer chains, the precursors to proteins and nucleic acids. The shallow pools of early Earth acted like natural reaction vessels, where evaporating edges concentrated chemicals while UV provided the energy to bond them. Even more intriguing, aerosols, tiny droplets lofted into the air by waves or geysers, could have served as miniature labs. As these droplets cycled between sunlight and shadow, their thin surfaces allowed UV to penetrate deeply, driving reactions before gravity pulled them back into the primordial soup. The key lies in timing and environment. Too much UV exposure destroys just enough builds. Modern analogs show how this balance might have worked. In places like Yellowstone's hot springs, researchers observe UV-driven chemistry in silica-rich waters, where mineral surfaces reflect and scatter light, creating pockets of milder radiation. Similarly, iron ions dissolved in ancient seas could have acted as molecular bodyguards, absorbing excess UV energy before it shattered delicate compounds. This delicate dance between creation and destruction wasn't a flaw, it was a filter, ensuring only the sturdiest molecular structures survived to evolve further. Critics once dismissed UV radiation as too chaotic for precise chemistry, but recent discoveries challenge that view. Certain wavelengths, like those around 250 nanometers, preferentially trigger specific polymerizations while leaving other bonds intact. It's as if sunlight came with built-in selectivity, favoring the formation of useful biomolecules over random junk. And when combined with tidal cycles, where molecules were repeatedly concentrated by evaporation during the day and protected at night, UV's dual nature becomes less of a contradiction and more of a regulated assembly line. The legacy of this process might still be visible today. Some of Earth's most ancient enzymes, like those that repair DNA damage, are remarkably efficient at handling UV-induced errors, a possible echo of life's origins in a world bathed in unfiltered sunlight. This theory doesn't just explain how molecules grew complex, it suggests that life's first tools were forged in the very fires that threatened to destroy them. And if that's true, the search for life elsewhere might need to focus not just on protected oases, but on worlds where radiation and chemistry perform the same delicate balancing act, turning harsh sunlight into the universe's most unexpected collaborator. Nothing jumpstarts chemistry quite like a cosmic collision. When a meteorite slams into a planet at tens of thousands of miles per hour, it doesn't just leave a crater. It creates a fleeting crucible of unimaginable heat and pressure. These extreme conditions, once thought to obliterate organic material, might have been the universe's most violent yet effective chemistry labs. Take the Sudbury Basin in Canada, a 2-billion-year-old impact scar stretching over 150 kilometers wide. Within its rocks, scientists found not just shattered minerals, but something astonishing: microscopic carbon spheres rich in complex organic molecules. These weren't contaminants from later life, they were forged in the fiery aftermath of the impact itself, preserved like cosmic fossils in the crater's bones. The process works like nature's own pressure cooker. When a meteorite strikes, it compresses the air and ground beneath it so violently that temperatures momentarily exceed those on the sun's surface. This energy doesn't just vaporize rock, it tears apart simple molecules like carbon dioxide and nitrogen, freeing atoms to recombine into entirely new forms. Shockwaves radiating outward create secondary hotspots where pressure remains intense, but temperatures drop just enough for delicate organics to stabilize. Simulations show these conditions can produce everything from amino acids to polycyclic aromatic hydrocarbons, molecules that form the scaffolding for more complex chemistry. What makes this theory so compelling are the real-world examples. The Murchison meteorite, famous for its organic bounty, shows signs of having endured impacts before landing on Earth. Its fractures are lined with clays that could only form under extreme heat and pressure, the same environments where scientists now suspect some of its amino acids were synthesized. Even more telling, the Rise crater in Germany contains layers of impact glass peppered with organic residues, proving that collisions didn't just deliver pre-made molecules but actively cooked them on site. Critics once dismissed impacts as too destructive, but nature thrives on paradox. While the initial shockwave incinerates, the aftermath creates something unexpected: hydrothermal systems. As the crater cools, groundwater seeps into fractured rock, heated by residual geothermal energy. These systems can persist for thousands of years, offering a Goldilocks zone where impact-generated molecules can further evolve. The Horton crater in the Canadian Arctic demonstrates this perfectly. Its ancient hydrothermal veins contain sulfur-rich minerals known to catalyze organic reactions, hinting at a multi-stage process where destruction gives way to creation. The implications stretch beyond Earth. Mars's vast impact basins show evidence of similar hydrothermal activity, and samples from asteroid Ryugu reveal organic molecules clustered in impact-shocked regions. It's as if the universe has been using collisions as a universal toolkit, forging complexity wherever rocks meet at cosmic speeds. This theory doesn't just redefine how life's ingredients could form. It suggests the most catastrophic events in the cosmos might secretly be its most creative. And if that's true, the chaotic early solar system wasn't a barrier to life's emergence, but perhaps its essential collaborator. Beneath Earth's restless surface, where tectonic plates grind and colossal forces reshape continents, another stage for life's origin story might have been hiding in plain sight. Subduction zones, those churning junctions where one plate dives beneath another, create conditions so extreme they defy imagination. Here, rock doesn't just melt, it transforms under pressures hundreds of thousands of times greater than sea level, temperatures soaring past 1,000 degrees. Yet within this seemingly inhospitable realm, a radical idea takes shape. That crushing force could have been the unseen hand guiding simple molecules toward complexity. The magic lies in how pressure alters chemistry's rules. At surface conditions, many organic reactions are sluggish or impossible. But deep underground, pressure acts like a molecular sculptor, bending and squeezing atoms into configurations that would never form otherwise. Picture carbon dioxide, a gas we exhale without thought. Under extreme pressure, it can behave like a liquid solvent, dissolving minerals and facilitating reactions between compounds that would otherwise ignore each other. Lab experiments using diamond anvil cells devices that replicate subterranean pressures have shown methane transforming into ethane and even benzene, the ring-shaped building block of more complex organics. It's as if the Earth's weight itself became a chemist forging bonds through brute force. What makes subduction zones uniquely promising are their dynamic gradients. As oceanic plates descend, they carry water-rich minerals downward, only to release that water when pressure cooks it out. This creates fluid-filled pockets at specific depths, where temperatures and pressures hit a sweet spot for organic synthesis. Japan's Shimanto Belt, a fossilized subduction zone, offers tantalizing clues. Rocks there contain microscopic carbon pockets with isotopic signatures suggesting biological origins, yet these rocks form deeper than any known life could survive. Some researchers propose these signatures might instead trace to probiotic chemistry, where pressure and heat acted as proxies for early enzymes. The most compelling evidence comes from serpentinization, a process where water reacts with mantle rock under pressure to produce hydrogen and simple organics. Modern analogs like the Lost City hydrothermal field thrive on this chemistry, but its roots may reach much deeper. Simulations show that subducting plates could have generated vast subsurface networks of these reactions, funneling organics upward through fractures over millions of years. Unlike fleeting surface events, these underground factories operated continuously, their products accumulating in crustal reservoirs where subsequent reactions could refine them. Critics argue that deep Earth molecules face a gauntlet of destruction as they rise toward the surface, but nature is full of surprises. Certain mineral structures, like the layered lattices of clays or iron-nickel sulfides, can shield delicate organics during their ascent. Others note that high-pressure syntheses often produce unusually stable molecules, like branched hydrocarbons that resist breakdown. These traits suggest that what emerged from the depths wouldn't just be random debris, but pre-selected for resilience, a molecular survival of the fittest. The implications ripple beyond our planet. Mars's extinct subduction zones or Europa's ice-crusted ocean might harbor similar high-pressure nurseries. This theory reframes life's origins not as a surface accident, but as a planetary-scale process with Earth's interior acting as a slow, relentless alchemist. It's a reminder that life's building blocks might not have been forged in sunlight or lightning, but in the silent darkness below, where pressure and time performed the universe's most patient chemistry experiment. The rhythmic rise and fall of tides might hold the key to one of chemistry's oldest mysteries: how scattered molecules gathered enough to spark life. Picture Earth's early coastlines, where crashing waves left behind shallow pools that baked under the sun before the next high tide rushed in. These weren't just puddles, they were nature's evaporating dishes, each cycle concentrating dilute organic soups into something far more potent. The magic lies in repetition. As water retreated, amino acids and other building blocks became trapped in shrinking pockets of brine, pressed together like commuters in a crowded train. And when the tide returned, it didn't just refill these pools, it brought fresh ingredients, resetting the stage for another round of molecular mingling. Lab experiments revealed just how powerful this push and pull could be. Scientists simulating tidal environments have watched simple amino acids like glycine link into chains when subjected to wet-dry cycles. Without these fluctuations, the same molecules drift aimlessly, too dilute to react. But as water evaporates, two things happen. Molecules crowd together, increasing collision rates, and the remaining water becomes saltier, creating ionic conditions that nudge certain reactions forward. Some studies show these cycles can even select for specific peptides, favoring structures that resist evaporation-induced damage. It's as if the tides themselves were curating the first molecular drafts of life, discarding fragile combinations while amplifying the robust ones. The real breakthrough came when researchers realized wet-dry cycles do more than concentrate, they actively guide chemistry. In 2018, a team at the University of Strasbourg demonstrated that alternating hydration could drive the formation of beta sheets, a key protein folding pattern. These sheets, in turn, act as templates, encouraging other molecules to align and bond in similar configurations. The implications are staggering. Tidal pools weren't just mixing bowls. They were molecular classrooms where simple compounds learned to self-organize. Even more striking, volcanic coastlines could have added geothermal heat to the equation, creating temperature gradients that further turbocharged reactions during low tide. Critics once dismissed tidal pools as too transient for meaningful chemistry, but nature thrives on rhythms. Modern analogs like Chile's Atacama Desert, where rare rains trigger explosive microbial activity in salt flats, show how episodic wetness can sustain complexity. And tidal cycles offer something rare in origin theories, a built-in timer. Unlike continuous environments where reactions stall at equilibrium, the ebb and flow of tides provide natural pulses of energy, preventing stagnation. This might explain how early polymers avoided degradation, with each dry phase locking in progress before the next wave brought renewal. What makes this theory so elegant is its universality. Any moon or planet with liquid water and tidal forces, whether from a nearby star or a massive neighbor like Jupiter, could host similar environments. Europa's icy crust, flexed by tidal stresses, might hide brine reservoirs where this very process unfolds today. And on Earth, the legacy of these ancient pools might linger in our cells' osmotic rhythms, echoes of a time when life's first whispers synchronized with the moon's pull. The tides that shaped our coastlines could have also shaped life itself, one evaporating droplet at a time. Deep beneath Earth's surface, where sunlight never reaches, another invisible force might have been quietly powering the chemistry of life: radioactivity. Imagine ancient rocks laced with uranium and thorium, their atoms slowly disintegrating over millennia. Each decay event releases a tiny burst of energy, not as dramatic as lightning or volcanic eruptions, but relentless, a slow burn that could have turned ordinary water and minerals into molecular workshops. This is radiolysis, a process where radiation splits water molecules into highly reactive fragments like hydrogen radicals and hydroxyl ions. These fragments don't just vanish, they become molecular matchmakers, attacking nearby compounds and forging new bonds in their wake. Laboratory experiments reveal how transformative this energy can be. When scientists simulate radioactive environments by exposing water and simple gases to gamma rays, a proxy for decay energy, they observe organic molecules forming within hours. Some studies have even produced acetic acid and formaldehyde under these conditions, compounds that serve as stepping stones to more complex chemistry. The key lies in radiation's ability to penetrate deep into rocks and sediments, reaching places where other energy sources like sunlight or lightning couldn't. Underground aquifers, shielded from surface chaos but bathed in radioactive decay, might have been ideal reactors for this quiet alchemy. Real-world evidence bolsters the theory. In places like South Africa's Moab Kotsong mine, where natural radioactivity is high, researchers have detected hydrogen-rich fluids and organic molecules thriving 2 miles underground. Even more compelling, certain mineral structures like zircon tiny time capsules trapped in ancient rocks preserve traces of radiation-driven chemistry dating back billions of years. These minerals act like cosmic breadcrumbs, hinting at environments where decay energy could have sustained reactions for eons. Critics argue that radiation destroys organic matter as often as it creates it, but nature is full of paradox. While high doses can shatter molecules, low-level radiation over long periods allows for a delicate balance, just enough energy to drive reactions without obliterating the products. Some minerals, like pyrite, even act as protective scaffolds, absorbing harmful radiation while channeling its energy into useful chemistry. It's a reminder that life's origins might not hinge on a single energy source, but on the interplay of many, where even the slow tick of a radioactive clock could have set the tempo for complexity. The implications stretch beyond Earth. Mars's subsurface, rich in radioactive elements like potassium and thorium, might harbor similar environments today. Europa's icy shell, flexed by tidal forces, could concentrate radioactive heat in pockets where chemistry simmers unseen. This theory doesn't just redefine where life might arise, it suggests the universe's quietest corners, humming with atomic decay, could be its most patient laboratories. And if that's true, the building blocks of life weren't just forged in fire and lightning, but in the gentle, persistent glow of rocks that refused to stay inert. Deep in the ocean's abyss, where scalding vents meet crushing darkness, chemistry might have taken its first steps toward life with the help of an unlikely collaborator, rust. The iron-sulfur world hypothesis turns conventional wisdom on its head, proposing that life didn't begin with delicate organic molecules floating freely, but with the gritty surfaces of minerals like pyrite, better known as fool's gold. These metallic crystals, formed where hot, mineral-rich fluids spew from the seafloor, could have served as nature's first enzymes, their jagged edges acting as molecular workbenches where simple compounds assembled into something far more complex. At the heart of this idea is a simple but profound shift in perspective. Instead of imagining life emerging from a soup of floating molecules, chemist Gunther Wechtersheuser envisioned chemistry anchored to solid surfaces, specifically the lattice-like structures of iron sulfide minerals. Picture the face of a pyrite crystal, its repeating grid of iron and sulfur atoms creating a mosaic of positive and negative charges. These charged patches could have attracted and stabilized key molecules like carbon monoxide and hydrogen sulfide, holding them in just the right orientations to react. Unlike random collisions in liquid, surface chemistry offers control, a way to channel chaos into order. Wechtersheuser's experiments in the 1990s brought this theory to life. By simulating vent conditions with iron and sulfur minerals in pressurized chambers, his team watched as carbon monoxide and hydrogen sulfide transformed into acetic acid, a molecule central to metabolism, without any biological enzymes. The minerals didn't just sit there, they actively participated, their surfaces acting like primitive versions of the protein catalysts found in modern cells. Even more strikingly, these reactions generated small amounts of energy, hinting at how early chemistry could have powered itself forward. The brilliance of this hypothesis lies in its self-reinforcing logic. As reactions produced more organic molecules, some would stick to the mineral surfaces, creating layers that further refined subsequent chemistry. Over time, these coatings could have grown complex enough to peel away as primitive membranes, forming the first protocells. Modern hydrothermal vents support this idea. Their chimneys often host thriving microbial communities that derive energy from iron-sulfur reactions, as if echoing ancient processes. Critics initially dismissed the iron-sulfur world as too limited, arguing that surface-bound chemistry couldn't explain life's full complexity, but recent discoveries have added nuance. Some lab experiments show iron-sulfur minerals can catalyze the formation of peptides and even nucleotides, the building blocks of RNA. Others reveal how mineral pores could have concentrated molecules, creating microenvironments where different reactions specialized. And in a stunning twist, certain iron-sulfur enzymes in modern cells still contain mineral-like clusters at their core, a possible molecular fossil of this metallic origin. What makes this theory so compelling isn't just the chemistry, it's the narrative. Iron-sulfur surfaces offer a bridge between geology and biology, turning inert rock into an active participant in life's origin story. They provide a solution to one of the greatest puzzles: how early molecules organized themselves without modern cellular machinery. The answer might have been beneath our feet all along, written not in the language of biology textbooks, but in the silent, metallic glint of minerals that refuse to stay lifeless. And if that's true, the same processes could be unfolding right now on ocean worlds like Enceladus, where hydrothermal activity meets iron-rich cores, proving that life's beginnings might owe as much to stone as to stardust. Imagine a world where tiny oil droplets in water held the secret to life's first fragile experiments. This isn't science fiction, it's the lipid membrane encapsulation theory, a dazzling idea that suggests the first step toward cells wasn't complex chemistry, but something as simple as soap bubbles. In the chaos of early Earth's waters, fatty molecules like lipids could have spontaneously formed microscopic spheres, creating natural containers that shielded delicate reactions from the outside world. These weren't true cells yet, but they offered something revolutionary: order. Inside these protective bubbles, scattered molecules suddenly had a chance to interact without being diluted or torn apart by waves or radiation. It's like the difference between trying to cook soup in a hurricane versus a sealed pot. The ingredients finally had a fighting chance to combine. Laboratory experiments reveal just how easily this could happen. When researchers mix certain lipids like those found in meteorites or simulated prebiotic conditions with water, the molecules self-assemble into hollow spheres called vesicles. Some even grow and divide on their own, mimicking basic cellular behaviors without any genetic instructions. The magic lies in lipid chemistry. Their dual nature, with water-loving heads and oil-loving tails, drives them to form stable membranes spontaneously. In 2018, a team at the University of Strasbourg demonstrated that these vesicles can selectively trap molecules inside, concentrating them up to 1,000 times more than the surrounding water. This concentration effect turns a quiet pond into a bustling molecular marketplace, dramatically increasing the odds of meaningful collisions. But lipid membranes did more than just protect her, they actively shaped evolution. Modern cell membranes are studded with proteins that control what enters and exits, but early vesicles might have used simpler tricks. Certain minerals, like silica or pyrite, can embed themselves in lipid layers, creating makeshift pores that allow nutrients in while keeping vital molecules trapped. Other studies show that temperature fluctuations cause vesicles to briefly breathe, opening tiny gaps that could have allowed primitive exchange with the environment. Over time, the vesicles that best maintained this balance, keeping good molecules in and bad ones out, would have outcompeted their less efficient neighbors. It's natural selection at the molecular level, with lipid bubbles acting as the first arenas for life's chemical competition. The most compelling evidence comes from extreme environments. Deep-sea hydrothermal vents, where hot and cold waters mix chaotically, are teeming with lipid-like molecules that form stable vesicles even under harsh conditions. Some of these vesicles contain iron sulfide minerals, hinting at a possible link between the iron-sulfur world and membrane encapsulation. Even more striking, analysis of meteorites like the famous Murchison specimen reveals lipids with branched structures, exactly the kind that form the most stable membranes. This suggests the universe might be preloaded with the ingredients for cellular boundaries, waiting for the right conditions to assemble them. What makes this theory so elegant is its universality. Unlike hypotheses tied to specific environments like tidal pools or volcanic vents, lipid encapsulation could have happened anywhere there was water and organic material, on Earth, Mars, or even Saturn's moon Enceladus. And the legacy of these early bubbles might still be with us. Modern cell membranes bear an uncanny resemblance to those simple vesicles, as if our biology never forgot its humble beginnings. The next time you wash your hands and see soap bubbles glisten, remember, the same physics that creates those fleeting spheres might have once cradled the universe's first experiments in turning chemistry into life. Imagine floating through the void between stars, where specks of dust no larger than a virus drift in the darkness. These seemingly insignificant particles, cosmic dust grains, might have been the universe's earliest chemistry labs. In the frigid expanse of interstellar space, where temperatures hover just a few degrees above absolute zero, chemical reactions should grind to a near halt. Yet, observations reveal these grains are coated with complex molecules, from water ice to formaldehyde and even amino acids. How does chemistry thrive in such a frozen wasteland? The answer lies in the dust itself. Each grain acts like a microscopic workbench, its surface providing a stage where atoms and molecules can meet and bond. In the emptiness of space, free-floating molecules rarely collide with enough energy to react, but when they stick to a dust grain, everything changes. The grain's surface holds them in place, allowing weak forces to bring them close together like strangers nudged into conversation at a crowded party. Ultraviolet light or cosmic rays then provide the final spark, injecting just enough energy to forge new bonds without vaporizing the delicate products. Telescopes have caught this process in action, detecting organic molecules like methanol and acetonitrile clinging to dust in interstellar clouds. Some of these grains, later incorporated into comets and asteroids, could have delivered their molecular cargo to young planets like Earth. The real breakthrough came when scientists recreated these conditions in labs. By chilling vacuum chambers to near absolute zero and coating surfaces with ice mixtures mimicking interstellar dust, they watched simple molecules like carbon monoxide and ammonia transform into complex organics under simulated starlight. Even more astonishing, some experiments produced ribose, the sugar backbone of RNA, suggesting cosmic dust might have contributed not just life's building blocks, but its very blueprints. These findings align with data from missions like Rosetta, which found organic rich dust clinging to Comet 67P. What makes dust grains so effective isn't just their surfaces, it's their imperfections. Tiny cracks and pores trap molecules, creating pockets where reactions can proceed sheltered from destructive radiation. Some minerals, like silicates or graphite, even conduct faint electrical charges, acting as catalysts to lower the energy needed for bonds to form. Modern astrochemical models suggest that without these microscopic platforms, the universe's molecular diversity would be far poorer. The implications stretch beyond our origins. If dust grains catalyzed chemistry in our solar system, The same process could be unfolding right now in the Orion Nebula or the dusty disks around newborn stars. Every speck of interstellar dust might be a silent factory, quietly assembling the ingredients for life wherever it drifts. And when those grains finally settle onto planets, they carry with them the universe's most precious gift, the seeds of complexity forged in the coldest depths of space. Above Earth's turbulent surface 4 billion years ago, a thick orange haze might have hung like a cosmic veil, not just blocking sunlight, but actively shaping the chemistry below. This photochemical smog model draws inspiration from Saturn's moon Titan, where nitrogen and methane brew an organic, rich atmosphere under the sun's faint glow. On early Earth, similar conditions could have created more than just a murky sky. They might have formed a planetary-scale reactor where simple gases transformed into life's precursors high above the ground. Unlike the familiar smog of modern cities, this primordial haze wasn't pollution. It was a creative force. Ultraviolet light breaking apart methane and nitrogen molecules would have spawned a cascade of reactive fragments like acetylene and hydrogen cyanide. These fragments, instead of dispersing, would have clumped into tiny organic aerosols, suspended in the atmosphere like microscopic chemical factories. Lab experiments simulating these conditions produce something astonishing. When irradiated under early Earth gas mixtures, these smog particles generate amino acids and nucleotide bases, the very letters of life's genetic alphabet, right in the air. The smog's dual role is what makes this theory so compelling. While it filtered harmful UV radiation, protecting delicate molecules forming in oceans below, its own layered structure acted like a distillation column. Heavier organic particles would have slowly rained down, delivering a steady supply of probiotic material to the surface. Meanwhile, lighter compounds remained aloft, undergoing further reactions in the upper atmosphere. This constant cycling between sky and earth, destruction and renewal, could have provided both the ingredients and the time needed for complexity to emerge. Critics once dismissed the idea, arguing that Earth's early atmosphere lacked enough methane to sustain Titan-like haze. But recent geochemical models suggest volcanic outgassing, and methane-producing microbes could have maintained methane levels far higher than today. And the evidence isn't just theoretical. Analysis of ancient zircon crystals reveals trapped carbon isotopes suggestive of atmospheric organic synthesis, while the Curiosity rover's discovery of organic rich smog particles in Martian soil hints that this process might be a planetary commonplace. The most tantalizing clue comes from how these aerosols behave. Under certain conditions, they spontaneously assemble into membranous vesicles, microscopic bubbles resembling primitive cells. Imagine trillions of these organic droplets floating in the ancient sky, each one a potential cradle for chemistry. When they finally settled into tidal pools or clay-rich soils, they wouldn't just bring raw materials, they'd deliver partially assembled molecular workshops ready for the next steps toward life. This vision transforms our picture of early Earth from a water world under clear skies to a shrouded laboratory where the air itself pulsed with chemical potential. And if smog could nurture life's beginnings here, might the same be true for hazy exoplanets orbiting distant stars? The answer could be written not in rock or ice, but in the dim orange glow of atmospheres we've only begun to explore. Geothermal pools are nature's slow cookers, simmering with chemical potential in ways no other environment can match. Unlike static ponds or chaotic ocean surfaces, these bubbling cauldrons offer something extraordinary: cycles. Picture a hot spring in Earth's early days, where volcanic activity caused water levels and temperatures to rise and fall like a slow, steady breath. Each fluctuation wasn't just a change, it was an opportunity. When water levels dropped, molecules concentrated against mineral edges. When temperatures spiked, bonds broke and reformed in new configurations. Then, as conditions cooled again, the most stable structures survived, ready for the next round of refinement. This rhythmic dance could have turned simple chemistry into complex assembly, one gentle pulse at a time. Lab experiments reveal the surprising power of these cycles. Researchers at the University of Glasgow recreated geothermal pool conditions by alternately heating and cooling mixtures of amino acids and nucleotides. The results were startling. Molecules didn't just survive the changes, they thrived. Heating phases helped break weak bonds, clearing the way for stronger structures, while cooling phases allowed those new bonds to lock into place. Over hundreds of repetitions, some mixtures began forming peptide chains and RNA-like strands, as if the pools themselves were editing out molecular mistakes with each cycle. The key was time. Unlike lightning strikes or meteor impacts, geothermal cycles operate on geological timescales, offering countless iterations for chemistry to inch toward complexity. Real-world examples add weight to the theory. Yellowstone's Grand Prismatic Spring isn't just a tourist attraction, it's a living laboratory. The spring's concentric rings, each at different temperature and chemical makeup, function like a natural chromatography column, sorting molecules by their stability. Cyanobacteria thrive in the cooler outer edges, but the scalding center is far from barren. There, silica-rich waters create porous matrices where organic molecules can assemble protected from UV radiation. Similar environments in Iceland's geothermal fields host iron-rich clays that catalyze reactions, while minerals like sulfur and phosphorus act as molecular glue. Critics once dismissed geothermal pools as too niche for life's origins, but their true advantage lies in diversity. Not all pools are boiling cauldrons. Some are warm, mineral-laden seeps with gentle gradients. Others, like Chile's El Techo geysers, alternate between acidic and alkaline conditions as underground vents shift. This variability means no single molecule needed to survive all environments. Just find one niche where it could persist long enough to evolve. Over millennia, runoff could have carried successful combinations into neighboring pools, creating a network of chemical experimentation across entire geothermal fields. The legacy of these cycles might still be written in our cells. Modern heat shock proteins, which help organisms survive temperature swings, could be echoes of a time when life's precursors had to endure daily thermal roller coasters. Even more telling, some of the oldest known microbial fossils are found in ancient hydrothermal deposits, their spiral shapes preserved in silica like cosmic fingerprints. If geothermal pools were indeed life's first classrooms, their lessons were written in heat and time, a curriculum still being decoded in steamy basins around the world, and perhaps on distant planets where volcanic whispers stir the waters even now. Of all the elements in life's recipe, phosphorus might be the most underrated and the most mysterious. While carbon, hydrogen, and oxygen grab the spotlight, it's phosphorus that quietly powers the show, acting as the linchpin of energy transfer in every living cell. Think of ATP, life's universal energy currency. That tiny molecular battery relies on phosphorus bonds to store and release energy with precision. But here's the puzzle. How did this critical element, so scarce in Earth's early crust, become abundant enough to fuel life's first sparks? The answer might lie in places where geology and chemistry collided in spectacular ways. One compelling scenario points to meteorites. When scientists analyzed the Murchison meteorite, they found something unexpected. Phosphorus bound in reactive minerals like schrebersite, a compound far more soluble than the stubborn apatite locked in Earth's rocks. This extraterrestrial phosphorus could have dissolved readily in water, becoming available for prebiotic chemistry in ways Earth's native forms couldn't. Lab experiments back this up. When schrebersite is added, to Chinese letter 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 Chinese letter, it spontaneously reacts to form phosphorylated molecules, the precursors to ATP and even RNA's backbone. It's as if the universe delivered phosphorus in a pre-activated package, ready to plug into life's emerging circuitry. Yet meteorites alone might not tell the full story. Recent studies of ancient marine sediments reveal another twist. Hydrothermal vents could have been phosphorus factories. In these environments, superheated water leaches phosphorus from oceanic crust, while iron-rich minerals act like molecular sponges, concentrating it thousands of times above normal levels. At the Lost City hydrothermal field, a modern analog, researchers found chimney structures oozing with phosphorus-rich fluids, a hint that early Earth's vents might have served up this element alongside the organic buffet. The controversy lies in timing. Some geologists argue that phosphorus only became abundant after 2 billion years ago, when oxidative weathering freed it from mineral prisons. But life clearly needed it earlier. This paradox has led to radical ideas, like submerged continental shelves acting as phosphorus traps, where wave action and tidal cycles gathered the element into shallow, sunlit pools. Others propose that acidic volcanic rains dissolved enough phosphorus from early basalts to kickstart chemistry, even if global supplies were low. What makes phosphorus so special isn't just its role, it's its versatility. Unlike carbon or nitrogen, phosphorus can form high-energy bonds stable enough to store energy but weak enough to release it on demand. It also acts as a molecular glue, linking nucleotides into RNA or holding lipid membranes together. Some theories even suggest that life's first energy cycles didn't wait for ATP. They used simpler phosphorus compounds like pyrophosphate, still found in modern cells' deepest metabolic pathways. The search for phosphorus's origins isn't just about Earth. Mars rovers have detected phosphorus-rich minerals in Gale Crater, while Europa's icy shell may hide hydrothermal systems similar to Lost City. If phosphorus was indeed the silent architect of life's energy systems, its cosmic availability could redefine where we look for life beyond our planet. And that's the real revelation. Sometimes the universe's quietest elements hold the loudest secrets. Among all the molecules that could have kick-started life, RNA stands out as the ultimate multitasker, a molecule that can store genetic information like DNA and catalyze reactions like a protein. This dual talent forms the backbone of the RNA world hypothesis, the idea that before DNA or proteins existed, life ran on RNA alone. But how did such a sophisticated molecule emerge from the chemical chaos of early Earth? The answer might lie in the very theories we've explored: hydrothermal vents, cosmic delivery, or even tidal pools, all converging to create the perfect conditions for RNA's precursors to take shape. Picture a world where smaller, simpler molecules began experimenting with self-replication. Ribonucleotides, the building blocks of RNA, are complex, but they might have started as fragments, just a sugar ribose clinging to a phosphate and a base. Lab experiments show these components can form under plausible early Earth conditions. In simulated hydrothermal vents, for instance, mineral surfaces act like molecular scaffolds, guiding ribose and phosphate to link up. Even more compelling, certain clays not only concentrate these molecules but also nudge them into chains, creating RNA-like strands without any biological help. It's as if the Earth's geology was pre-programmed to assemble these puzzle pieces. The real magic, though, lies in RNA's ability to fold back on itself. Unlike DNA's stiff double helix, RNA can twist into intricate shapes, some of which function like primitive enzymes. Scientists have even discovered ribozymes, RNA molecules that can cut, splice, and crucially copy other RNAs. In a groundbreaking experiment, researchers engineered a ribozyme that could replicate part of its own sequence, a tantalizing glimpse of how self-replication might have begun. If a single molecule could store information and copy itself, the leap from chemistry to biology suddenly seems far less daunting. Critics argue that RNA is too fragile to have survived early Earth's harsh conditions, but nature has a way of protecting what matters. Ice-covered ponds or mineral-rich vents could have shielded delicate strands, while wet-dry cycles might have helped them grow longer through repeated dehydration. Some theories even suggest that RNA's precursors weren't free-floating but bound to mineral surfaces where they could replicate without drifting apart. And if cosmic dust or meteorites delivered pre-made nucleobases, the assembly process would have had a head start. The RNA world hypothesis doesn't just explain life's origins, it reshapes how we see the universe's potential. If RNA could emerge from simple chemistry, then the path from molecules to life might be simpler and more universal than we ever imagined. Every strand of RNA in your cells today might be a descendant of those first tentative experiments in self-replication, a living fossil of biology's earliest days. And if that's true, the search for life elsewhere might not need DNA as a signpost, just the whisper of RNA's ancient, versatile chemistry echoing through the cosmos. What if the division between proteins and genetic material wasn't always so clear? The peptide nucleic acid coevolution theory paints a radically different picture of life's origins. One where these molecules didn't emerge separately, but grew up together, each stabilizing and enhancing the other like cosmic dance partners. Imagine a world where the first tentative steps toward biology weren't taken by RNA alone or proteins in isolation, but by molecules that blurred the line between the two. This isn't just a compromise between competing theories, it's a paradigm shift that could explain some of biochemistry's deepest mysteries. Modern cells keep proteins and nucleic acids in separate roles. DNA stores information, proteins do the work. But early chemistry might not have been so tidy. Lab experiments reveal something astonishing. When amino acids and nucleotides mix under simulated probiotic conditions, they don't just coexist, they collaborate. Certain peptides, even short ones, can wrap around RNA strands like molecular Velcro, protecting them from degradation while improving their ability to fold into functional shapes. In return, RNA provides a scaffold that helps peptides organize into more stable structures. It's a symbiotic relationship baked into their very chemistry, suggesting this partnership might predate life itself. The most compelling evidence comes from hybrid molecules called peptide nucleic acids, or PNA. These bizarre chimeras have peptide backbones but nucleotide side chains, as if someone spliced proteins and DNA together. When scientists synthesize PNAs in labs, these molecules exhibit uncanny properties. They bind to RNA more tightly than RNA binds to itself, and they resist heat and chemical damage far better than either pure peptides or nucleic acids. Some researchers speculate PNAs could have been evolutionary stepping stones, acting as molecular bridges between the RNA world and the protein-dominated life we know today. But how could such partnerships form spontaneously? Hydrothermal vents provide a plausible stage. Their porous mineral structures create microcompartments where peptides and nucleotides could concentrate together, while temperature gradients drive cycles of bonding and unbonding. Experiments show that when amino acids flow through heated, mineral-rich channels mimicking vent environments, they spontaneously form peptides that bind to RNA-like molecules. Even more strikingly, some of these peptide RNA complexes display primitive catalytic activity, hinting at how early biochemistry might have bootstrapped itself into existence. Critics argue that coevolution requires too many coincidences. Why would both molecule types emerge simultaneously? Yet nature loves redundancy. Tidal pools could have concentrated nucleotides while volcanic lightning synthesized amino acids, bringing both together through rainfall and river flow. And the benefits are undeniable. RNA's fragility vanishes when peptides act as molecular bodyguards, while peptides gain direction from RNA's information-storing capacity. This mutualism solves one of origin of life biology's biggest headaches: how complexity could accumulate before modern enzymes evolved to protect and replicate genetic material. The implications ripple across astrobiology. If life's blueprint relied on peptide nucleic teamwork from the start, we might need to broaden our search for extraterrestrial chemistry. Instead of hunting solely for RNA or amino acids on Mars or Europa, we should look for hybrid molecules or environments where both could naturally mingle. The universe might be full of molecular odd couples quietly rewriting the rules of chemistry in ways we're only beginning to imagine. And if that's true, the boundary between geology and biology could be far messier and far more interesting than we ever dreamed. One of the most perplexing quirks of life's chemistry isn't what molecules it uses, but how they're twisted. Every amino acid in your body has the same eerie left-handed orientation, while every sugar in your DNA coils to the right. This obsession with directionality, called chirality, shouldn't exist in a universe where molecules normally form in equal left and right-handed versions. Yet somehow life chose sides, and the reason behind this bias might be etched in starlight, written in stone, or even hidden in the spin of subatomic particles. The puzzle starts with symmetry. When chemists synthesize amino acids in labs without biological influence, they get a 50-50 mix of left and right-handed versions. But nature threw that balance out the window. One theory points to polarized starlight as the cosmic sculptor. As light travels through interstellar dust clouds, it can become polarized, vibrating in a specific orientation. Experiments show that when this polarized light interacts with probiotic molecules, it selectively breaks down one chiral form over the other. The Orion Nebula, a stellar nursery brimming with such polarized light, has even been found to contain amino acids with a slight but measurable bias toward life's preferred handedness. It's as if the universe tipped the scales before Earth even formed. Yet starlight isn't the only suspect. Certain minerals have surfaces that act like molecular racetracks, favoring one chiral direction over another. Quartz crystals, for instance, come in left and right-handed varieties, and their jagged atomic edges can selectively absorb or catalyze specific chiral forms. In lab simulations, amino acids interacting with chiral quartz surfaces have shown up to 15% bias, a small but potentially catalytic nudge toward homogeneity. Even more intriguing, clays like kaolinite, which littered Earth's early tidal flats, can amplify these biases through repeated wet-dry cycles, concentrating one form while washing away its mirror image. The plot thickens when we consider radioactivity. Some isotopes, like potassium-40, emit beta particles with a slight spin preference, a phenomenon called parity violation. Though the effect is minuscule, over millions of years in a probiotic soup, this weak nuclear force could have gradually skewed molecular handedness. Experiments with radioactive cobalt isotopes have demonstrated this principle, producing amino acid imbalances that echo life's preferences. It's a reminder that life's asymmetry might be written into the fabric of physics itself. What makes this mystery so pivotal isn't just the why, it's the so what. Chirality isn't a cosmetic quirk, it's essential for life's machinery. Enzymes, the workhorses of biology, rely on precise molecular fits like locks and keys. A right-handed enzyme can't process a left-handed amino acid, meaning mixed chirality would grind metabolism to a halt. Early Earth might have been a battleground where slight imbalances, whether from starlight, minerals, or atomic spin, snowballed into total domination by one chiral faction. The echoes of this selection might still resonate across the cosmos. When the Rosetta probe analyzed Comet 67P, it found glycine, an amino acid, but couldn't determine its chirality. Future missions could hunt for this bias as a signpost for life's potential elsewhere. After all, if the universe has a preferred handedness, then life's leanings might not be an accident, but a cosmic signature waiting to be decoded. And that would mean the twist in life's molecules isn't just a footnote. It's a clue to the universe's hidden symmetry-breaking rules written in the very stuff we're made of. Hydrogen cyanide might sound like the last molecule you'd associate with life. It's infamous as a deadly poison today. But 4 billion years ago, this simple compound could have been the unsung hero of chemistry's greatest leap. Picture Earth's early skies thick with volcanic gases and bombarded by ultraviolet light. In that chaotic mix, hydrogen cyanide molecules would have formed constantly, their triple-bonded structures cracking open under the sun's glare only to reform in endless cycles. What makes this molecule special isn't just its abundance, it's its astonishing versatility. Under the right conditions, HCN doesn't just linger, it transforms, linking together into chains that resemble proteins' backbones, as if the universe encoded a shortcut to complexity in its very structure. Laboratory experiments reveal how this molecular alchemy might have worked. When scientists simulate early Earth conditions with hydrogen cyanide and water, something remarkable happens. The molecules don't stay small. They polymerize, forming long chains called polyamidines that can later rearrange into polypeptides, the cousins of modern proteins. The key is concentration. In dilute environments, HCN floats harmlessly, but in evaporating tidal pools or on the surfaces of volcanic ash particles, these molecules get pushed together, forced into reactions that would otherwise never occur. Add a pinch of ammonia or formaldehyde, both plausible early atmospheric components, and the process accelerates, creating nitrogen-rich polymers that could have served as primitive enzymes. The real breakthrough came when researchers realized hydrogen cyanide's potential extends far beyond proteins. In 1961, chemist Joan Oro demonstrated that HCN solutions could spontaneously generate adenine, one of the 4 nucleobases in DNA and RNA. This discovery tied HCN directly to life's genetic machinery, suggesting a single molecule might have contributed to both metabolism and replication. Modern astrochemistry supports this. Telescopes have detected hydrogen cyanide in molecular clouds, comet tails, and even the atmospheres of distant exoplanets, proving its cosmic ubiquity. Critics point out that HCN is notoriously unstable in water, but nature rarely works in isolation. Mineral surfaces like clays or iron sulfides could have stabilized the molecule long enough for polymerization to occur. Some volcanic sediments even contain porous structures where HCN would be protected from rapid breakdown while still interacting with other chemicals. And here's the twist: hydrogen cyanide's very toxicity might have been an asset. By reacting violently with other compounds, it could have driven the kind of energy-intensive reactions needed to build complexity, acting less like a poison and more like a chemical spark plug. The legacy of this molecule might still be etched in our cells. Modern metabolic pathways like the Krebs cycle contain echoes of HCN chemistry, citrate and succinate molecules bearing structural resemblances to cyanide derivatives. Even more striking, certain deep-sea microbes still use hydrogen cyanide in their metabolism, as if clinging to ancient molecular tools. This theory doesn't just rewrite HCN's story, it turns a cosmic villain into a potential architect of life, proving that in chemistry's grand theater, yesterday's poison could be tomorrow's foundation. Formaldehyde might seem like an unlikely hero in life's origin story, a simple molecule best known today for preserving specimens in jars. But 4 billion years ago, this unassuming compound could have been the linchpin in one of biochemistry's most crucial leaps, the formation of sugars. Picture Earth's shallow pools, rich with formaldehyde washed in from the atmosphere or delivered by meteorites. Under the right conditions, these molecules don't just float idly, they link together in a dazzling cascade called the Formose reaction, transforming from single carbon units into the sweet building blocks of RNA and metabolism. The magic begins when formaldehyde meets a catalyst, often something as ordinary as a mineral like calcite or a speck of clay. In lab experiments mimicking early Earth conditions, scientists observe something extraordinary. Formaldehyde molecules spontaneously condense into glycolaldehyde, a 2-carbon sugar, which then rapidly snowballs into longer chains like ribose, the backbone of RNA. The reaction isn't just efficient, it's eerily selective. certain minerals like borates found in ancient hot springs act like molecular traffic cops, steering the chaos toward useful sugars while suppressing side reactions. It's as if the Earth's geology had built-in quality control for probiotic chemistry, but the real brilliance of the Formose reaction lies in its versatility. Unlike rigid laboratory syntheses, this process thrives under a range of conditions: warm alkaline pools, tidal flats where wet-dry cycles concentrate reactants, even the icy surfaces of comets where formaldehyde is abundant. Modern hydrothermal fields like Yellowstone's chocolate pots demonstrate this adaptability. Their iron-rich, mineral-laden waters naturally produce formaldehyde derivatives, hinting at how widespread these reactions could have been. Even more compelling when researchers simulate meteorite impacts in formaldehyde-rich ice mixtures, the resulting shockwaves trigger sugar formation, suggesting cosmic collisions might have jump-started the process. Critics once dismissed the Formose reaction as too messy, producing a tarry sludge alongside useful sugars. Yet nature rarely works in isolation. Recent studies reveal that minerals like hydroxylapatite, a common component of volcanic rocks, can filter out the desirable products, allowing ribose to accumulate while degrading unwanted byproducts. Other experiments show that ultraviolet light, often seen as destructive, can actually prune sugar chains into more stable forms, acting like a molecular sculptor. This interplay between synthesis and selection transforms the Formose reaction from a chemical curiosity into a plausible pathway for life's sugar supply. The implications stretch beyond Earth. The Rosetta mission detected glycolaldehyde, a Formose reaction intermediate, on Comet 67P, while ALMA telescopes have spotted the same molecule in interstellar clouds. If sugar formation is this universal, then the universe might be quietly sugaring up planets and comets wherever formaldehyde exists. And that's the real wonder. A molecule we associate with sterile labs could have been the universe's favorite candy machine, doling out the sweet ingredients for life's first experiments in chemistry. Sulfur might be the universe's most underrated chemical workhorse, a pungent yellow element that could have powered life's first energy cycles long before oxygen dominated the scene. Picture Earth's early oceans where volcanic vents spewed hydrogen sulfide into the water like a cosmic battery acid. This wasn't just pollution, it was fuel. Unlike today's oxygen-rich world where respiration rules, the first metabolic sparks might have crackled to life in sulfur-driven reactions, tapping into the element's talent for swapping electrons like molecular currency. Modern extremophiles bacteria thriving in scalding vents or acidic hot springs still run on this ancient playbook, offering us living snapshots of how sulfur could have turned geology into biology. The magic lies in sulfur's versatility. It can exist in multiple oxidation states, making it perfect for redox reactions, the electron transfers that power everything from your mitochondria to a car battery. In lab simulations of early vent environments, scientists watch as hydrogen sulfide reacts with iron or carbon dioxide to produce energy-rich compounds like thioesters. These molecules aren't just curiosities, they're the evolutionary cousins of modern metabolic staples like acetyl-CoA, the hub of your body's energy metabolism. It's as if life's first engines were built from sulfur's atomic gymnastics, with each reaction chipping away at the barrier between chemistry and biology. The real smoking gun comes from comparing ancient and modern sulfur cycles. Deep-sea vent microbes like Aquifex and Sulfolobus don't just tolerate sulfur, they thrive on it, using pathways that look like stripped-down versions of our own metabolic networks. Their enzymes often cluster around iron-sulfur minerals, echoing the mineral-catalyzed reactions proposed for early Earth. Even more telling, some of these organisms can switch between sulfur and oxygen as electron acceptors, suggesting metabolism's roots might stretch back to a time when sulfur was the go-to energy source. Not all sulfur chemistry happened underwater, though. Volcanic gas plumes could have lofted sulfur dioxide into the atmosphere, where ultraviolet light transformed it into reactive sulfite ions. Rain would have washed these compounds into tidal pools, creating land-based hotspots for sulfur-driven chemistry. Experiments show sulfite reactions can produce organic thiols, sulfur-containing molecules that could have protected early biomolecules from radiation or heavy metal toxicity. It's a reminder that sulfur's role wasn't just energetic. It might have been life's first antioxidant, shielding delicate chemistry while fueling its growth. The legacy of this sulfur world lingers in your cells. Modern mitochondria still harbor iron-sulfur clusters at the heart of their electron transport chains, like molecular fossils of those primordial reactions. And the unmistakable scent of volcanic hot springs, the rotten egg whiff of hydrogen sulfide, isn't just a geological quirk. It's a whiff of the chemistry that might have set the stage for life's first act, proving that even the universe's stinkiest element could be the unsung hero of our origins. So the next time you pass a steaming vent or catch a sulfurous breeze, remember, that smell might be the closest thing we have to time travel, a direct line back to the moment energy first learned to flow. Cosmic rays, those high-energy particles screaming through space at nearly light speed, might seem like nothing more than a celestial nuisance, but 4 billion years ago, these subatomic bullets could have been the universe's ultimate chemistry tutors, etching life's blueprints into Earth's atmosphere and icy crust. Imagine a young planet bombarded by protons and atomic nuclei from distant supernova, each impact delivering a concentrated burst of energy capable of tearing molecules apart, or stitching them together in entirely new ways. While sunlight and lightning get most of the credit for probiotic chemistry, cosmic rays operate on a different scale entirely, packing enough punch to trigger reactions no other energy source could match. Laboratory experiments reveal just how transformative these particles can be. When scientists simulate cosmic ray bombardment by firing protons or heavy ions at mixtures resembling early Earth's atmosphere or icy cometary surfaces, something astonishing happens. Simple molecules like carbon dioxide and nitrogen rearrange into complex organics, including amino acids and nucleobases. One study at the University of Sherbrooke used a particle accelerator to blast frozen mixtures of water, methanol, and ammonia, common ingredients in interstellar ice. The result, glycine and alanine, two of life's essential amino acids, formed in quantities that scaled with radiation dose. The process works like a molecular domino effect. Cosmic rays smash into ice, releasing secondary electrons that break chemical bonds, while the resulting fragments recombine into more stable and more complex structures. What makes cosmic rays uniquely powerful is their penetration. Unlike ultraviolet light, which only affects surface layers, or lightning, which is localized, cosmic rays can reach deep into ices or even underground water pockets. Modern analogs show this in action. In Antarctica's dry valleys, ice-bound organic compounds show radiation-induced changes identical to those seen in lab simulations, proving that cosmic rays don't just destroy, they rebuild. Even more compelling, meteorites like the famous Murchison specimen contain isotopes like beryllium-10, which form exclusively under cosmic ray bombardment, alongside a rich cocktail of organics. It's as if these space rocks recorded their own irradiation history, preserving the very process that might have jump-started their chemical complexity. The implications stretch far beyond Earth. Europa's icy crust, Saturn's rings, or even the frozen plains of Pluto could harbor similar radiation-driven chemistry. NASA Europa Clipper mission, set to launch soon, carries instruments specifically designed to detect organic signatures from cosmic ray processing in the Moon's surface ice. If life's precursors can form under such extreme conditions, then the universe's most inhospitable corners might secretly be its most productive labs. Critics argue that cosmic rays are too random, too destructive, to reliably build complexity. Yet nature thrives on balance. While a single cosmic ray can shatter molecules, the resulting fragments often stabilize in ice's crystalline matrix, protected long enough to find new partners. Some icy mixtures even exhibit a Goldilocks effect. Too little radiation does nothing, too much destroys, but just the right amount catalyzes a cascade of useful reactions. This fine-tuning suggests cosmic rays weren't just background noise. They were precise tools wielded by the universe to carve order from chaos. The legacy of this process might linger in our cells. Modern organisms, from bacteria to humans, rely on radiation-resistant enzymes to repair DNA damage, hinting at an ancient heritage shaped by cosmic bombardment. And when astronomers trace the faint glow of organic molecules in distant nebulae, they might be witnessing the same cosmic alchemy that once sprinkled Earth's chemistry set with stardust. So the next time you gaze at the night sky, remember, those silent streaks of invisible energy aren't just cosmic static. They could be the echoes of the universe's first attempts at writing the recipe for life. Borate minerals might seem like an obscure footnote in geology textbooks until you realize they could have been the unsung guardians of life's sweetest secret. Picture Earth's early oceans where delicate sugar molecules like ribose, the backbone of RNA, faced a brutal paradox. They were essential for life's first genetic code, but chemically unstable, prone to crumbling into useless fragments within hours. Enter borates, humble minerals like borax or kernite, washing into ancient seas from volcanic springs. Their peculiar talent, acting like molecular bodyguards for sugars, shielding them from degradation long enough to join life's chemical symphony. The magic lies in boron's unique chemistry. Unlike most elements, boron readily forms compounds where it's electron deficient, craving interactions with other molecules. When dissolved in water, borates latch onto sugars like ribose, wrapping them in a protective embrace that stabilizes their fragile ring structures. Lab experiments reveal this vividly. When ribose is mixed with borate minerals under simulated early Earth conditions, its lifespan jumps from minutes to weeks. Some borate sugar complexes even resist breakdown at temperatures near boiling, a crucial trait for surviving hydrothermal environments. It's as if the Earth's crust provided its own preservation system, turning fleeting sugars into enduring building blocks. The smoking gun for this theory comes from California's Death Valley, where borate-rich deposits lie alongside ancient lake beds. Analysis of these minerals shows they could have concentrated in shallow evaporating pools 4 billion years ago, creating natural sugar nurseries. Even more compelling, when researchers recreated these environments in labs, borates didn't just protect ribose, they guided its formation. In formaldehyde-rich solutions mimicking the Formose reaction, borates suppressed chaotic side reactions, funneling chemistry toward biologically useful sugars. The minerals acted like molecular traffic cops, directing prebiotic traffic toward orderly complexity. But borate's role might extend beyond stabilization. Certain boron compounds catalyze the linkage of sugars into longer chains, a critical step for building RNA. In hydrothermal vent simulations, borate-loaded minerals like colemanite facilitate the bonding of ribose to phosphate, creating RNA-like strands without biological enzymes. This dual-function preserver and assembler hints at a deeper partnership between geology and biology. Modern cells still rely on boron for cell wall strength in plants and metabolic regulation in animals, as if echoing an ancient dependence. The implications stretch beyond Earth. Mars' Jezero crater, explored by the Perseverance rover, contains boron-bearing clays, while meteorites like the infamous Tagish Lake show boron enrichments alongside organic molecules. If borates truly were sugar's guardians, their presence on other worlds could signal environments ripe for life's molecular precursors. This theory transforms our view of early chemistry from a desperate scramble for stability to a finely tuned collaboration, where the right minerals met the right molecules at the perfect moment, turning fragility into the foundation for everything that followed. Long before ATP became life's universal energy currency, another molecule might have been powering the first sparks of biochemistry: polyphosphates. These chains of phosphate groups, found abundantly in volcanic rocks and hydrothermal vents, possess an almost magical ability to store and release energy with each bond. Picture Earth's early geothermal pools where superheated water leached polyphosphates from minerals like apatite, creating a simmering broth of energetic molecules ready to fuel the first steps toward life. Polyphosphates hold a unique advantage over modern energy carriers: they're rugged. Unlike delicate ATP, which requires intricate enzymes to remain stable, polyphosphate chains can withstand extreme heat, acidity, and radiation. In lab simulations mimicking ancient vent conditions, these molecules demonstrate an astonishing versatility. When mixed with simple organic compounds, they readily donate phosphate groups, jump-starting reactions that could lead to everything from nucleotide formation to peptide bonding. Some researchers have even observed polyphosphates acting as primitive catalysts, lowering the energy required for reactions much like modern enzymes do. The real magic lies in how seamlessly polyphosphates bridge geology and biology. Modern organisms still carry traces of this ancient energy system. Certain bacteria living in volcanic hot springs stockpile polyphosphate granules as emergency fuel reserves. Even human cells retain polyphosphate-dependent processes in our mitochondria, hinting at a deep evolutionary heritage. Experiments with volcanic rock show how easily these molecules could have formed naturally when apatite interacts with acidic hydrothermal fluids. It releases phosphate chains that concentrate in evaporating pools, creating natural batteries where probiotic chemistry could recharge endlessly. Critics once dismissed polyphosphates as too simple to drive complex biochemistry, but nature often builds sophistication from humble beginnings. Under the right conditions, these chains can grow dozens of units long, storing energy comparable to ATP bonds. Some theories suggest that early metabolic pathways might have relied on polyphosphate-driven cycles before evolving more efficient systems. The transition could have been gradual, first using mineral-derived polyphosphates, then learning to synthesize them, and finally developing the intricate ATP machinery we see today. This theory doesn't just explain life's energy origins, it reshapes how we search for life elsewhere. Mars' Jezero crater shows evidence of ancient phosphate deposits, while Saturn's moon Enceladus has hydrothermal activity that could be producing polyphosphates right now. If these molecules truly were the universe's first energy currency, then planets lacking complex organics might still harbor the spark of chemistry's greatest innovation, written not in carbon alone, but in the persistent, energetic bonds of phosphorus chains. Thick, iridescent slicks of oil floating on Earth's early oceans might seem like pollution to modern eyes, but 4 billion years ago, these hydrophobic layers could have been the universe's first molecular assembly lines. Picture vast stretches of primordial seawater dotted with patches of organic films, not unlike the rainbows you see in parking lot puddles today. These weren't random accidents of chemistry. They were dynamic interfaces where water-hating hydrophobic and water-loving hydrophilic molecules naturally sorted themselves, creating concentrated zones of reactivity. Unlike the dilute chaos of open water, these floating mats offered something revolutionary: organization. At the boundary between oil and water, molecules behaved differently. Hydrophobic compounds like certain fatty acids or polycyclic aromatics cluster together, shielded from the surrounding water, while charged or polar molecules align at the edges. This spontaneous sorting isn't just neat, it's functional. Lab experiments show that when amino acids or nucleotides are sprinkled onto simulated probiotic oil-water layers, they arrange into dense, orderly arrays. Some even link into chains under the gentle energy of sunlight or geothermal heat, as if the surface itself was guiding their assembly. The films act like molecular conveyor belts, keeping reactants close enough to interact while preventing them from drifting apart, a critical hurdle for early chemistry. The real magic happens when these films interact with their environment. Waves and wind would have stretched and compressed the oil patches, creating transient pockets of high pressure similar to how folding dough traps air bubbles. These mechanical forces could have driven condensation reactions, squeezing water molecules out between amino acids to form peptide bonds, or nudging nucleotides into RNA-like strands. Modern analogues exist in places like the Gulf of Mexico, where natural oil seeps create organic slicks hosting unique microbial communities adapted to the oil-water interface. These ecosystems hint at how life might have co-opted such environments early on, turning a passive film into an active scaffold. But hydrocarbon layers didn't just assemble molecules, they protected them. Ultraviolet light that would shatter delicate compounds in open water gets absorbed or scattered by the oil's tangled molecular nets. Certain hydrocarbons even act as primitive antioxidants, soaking up destructive free radicals before they can break apart nearby organics. This dual-role concentrator and protector makes these floating mats ideal incubators. Meteorite analyzers support this. Carbon-rich asteroids like Ryugu contain tholin-like compounds that form oily layers when mixed with water, suggesting the universe might be seeding planets with these ready-made reaction platforms. The implications ripple beyond Earth. Titan's methane lakes, with their own hydrocarbon cycles, could be hosting similar interfacial chemistry right now. Even on early Mars, where volcanic activity might have created temporary oil seeps in ancient lakes, these slicks could have offered a fleeting sanctuary for molecular complexity. What seems like a simple sheen on water might be one of the universe's most versatile tools, a self-assembling stage where chemistry took its first steps toward becoming biology, one oil droplet at a time. Earth's magnetic field today acts like an invisible shield, deflecting cosmic rays and solar winds, but 4 billion years ago, it might have played a far more subtle and surprising role, guiding life's first molecules into alignment. Picture a young planet, its magnetic field freshly generated by the churning of molten iron in the core. Above the surface, floating in tidal pools or clinging to mineral grains, delicate organic molecules could have responded to this force in ways we're only beginning to understand. While evidence remains scarce, the tantalizing possibility exists that Earth's magnetism nudged early chemistry toward order, acting as a silent director in life's molecular theater. The theory hinges on a peculiar property of certain molecules, their ability to act like tiny compass needles. Just as iron filings align along magnetic field lines, some organic compounds, especially those with metal ions or aromatic rings, exhibit weak magnetic sensitivity. In lab experiments, researchers have observed amino acids like tryptophan and tyrosine orienting themselves in strong magnetic fields, altering how they interact with neighboring molecules. Early Earth's field, though weaker than today's, was far more turbulent, with frequent reversals and fluctuations. These dynamic shifts could have created brief but intense local fields, particularly near volcanic regions rich in magnetic minerals like magnetite. Imagine hydrothermal vents spewing iron-rich particles into seawater, each grain becoming a microscopic magnet that amplified the planet's field, coaxing nearby organics into alignment. Critics argue that such effects would be too faint to matter in the chaos of early Earth, but nature often amplifies subtle forces over time. Recent studies of magnetotactic bacteria, which literally navigate using internal compasses made of magnetite crystals, show how profoundly biology can exploit magnetism. These microbes didn't invent magnetic sensitivity, they co-opted a pre-existing property of certain molecules. Even more intriguing, some RNA and DNA sequences fold differently under magnetic fields, hinting that genetic machinery itself might carry echoes of this ancient influence. The deepest mystery lies in symmetry, breaking how life's molecules developed uniform-handedness. Magnetic fields, when combined with other factors like polarized light or mineral surfaces, could have tipped the scales. Experiments with chiral molecules in magnetic fields show slight biases in reaction rates, suggesting magnetism might have worked in concert with other forces to push chemistry toward homogeneity. It's a reminder that life's origins may not hinge on a single dramatic event, but on the convergence of countless subtle influences, each nudging the needle toward complexity. While the evidence remains circumstantial, the implications are cosmic. If Earth's magnetic field played even a minor role, then exoplanets with similar dynamo activity might share this hidden advantage. Mars, with its dead core and feeble remnant fields, could have lost more than just an atmosphere. It might have missed a critical catalyst for life's delicate chemistry. And that's the real wonder. The same force that now shields us from space's fury might once have been the unseen hand that helped write life's first lines. Perhaps the most profound revelation from studying life's origins isn't that one environment won, but that the universe played every angle at once. Imagine Earth 4 billion years ago as a sprawling chemical laboratory where vents, tidal pools, volcanic plumes, and even interstellar dust all contributed their unique ingredients to the cosmic recipe. This combinatorial hotspot theory doesn't just broaden the story, it transforms it into a symphony of possibilities, where each setting added its own note to the melody of life's emergence. Take hydrothermal vents, where mineral-rich fluids and steep energy gradients forged simple molecules into complex chains. Meanwhile, on the sunlit surface, tidal pools concentrated these compounds through endless wet-dry cycles, while ultraviolet radiation acted as both sculptor and destroyer, refining mixtures through relentless selection. Above, meteorites and comets rained down pre-made organics from space, as atmospheric chemistry brewed its own concoctions in the skies. Even the frozen voids between stars played a role, with icy dust grains assembling molecules too fragile to form on Earth. No single environment could do it all, but together they created a network of chemical innovation, each filling gaps the others couldn't. The beauty of this mosaic lies in its redundancy. If one pathway failed, say, a volcanic eruption sterilized a vent system, others persisted. Tidal flats kept simmering, meteorites kept landing, and interstellar ices kept drifting. This wasn't just backup plans, it was nature's way of stacking the deck. Experiments at the University of Strasbourg highlight this resilience. When researchers combined products from vent simulations with those from UV-irradiated atmospheric samples, the resulting mixtures showed exponentially richer chemistry than either could produce alone. It's as if the planet itself was cross-pollinating its best ideas. Critics once dismissed such combinatorial models as overly complex, but modern astrobiology keeps proving otherwise. Mars rover data shows evidence of ancient hydrothermal and fluvial environments side by side, while Europa's ice-covered ocean likely hosts both tidal flexing and volcanic activity. Even Saturn's tiny moon Enceladus sprays plumes containing organic molecules alongside silica nanoparticles, a telltale sign of hot water rock interactions. The universe, it seems, prefers teamwork when it comes to crafting complexity. What emerges is a vision far more vibrant than any single origin story. Life's building blocks weren't forged in one crucible but assembled through a grand, chaotic exchange, a planetary-scale marketplace where molecules traded hands between environments, each adding value before passing them on. The polymers that formed in vents might have been polished in tidal pools, then delivered to clay-rich estuaries by rivers, with cosmic newcomers joining the mix all the while. This constant shuffling didn't just increase the odds, it allowed for iterative refinement, like a draft being edited by countless co-authors. The lesson goes beyond Earth. If combinatorial chemistry birthed life here, why not on ocean worlds with ice shells and rocky cores, or exoplanets where volcanic islands dot shallow seas? The universe's formula for life might not be a single recipe but a pantry of ingredients and techniques waiting for the right moment to mix. And that's the real wonder. The diversity of pathways isn't a complication. It's the universe's greatest shortcut, turning the improbable into the inevitable through the power of countless tiny collaborations. From the simmering chaos of Earth's primordial soup to the icy depths of interstellar space, each of these 30 theories offers a unique lens on one of the universe's greatest mysteries: how lifeless molecules cross the threshold into biology. Hydrothermal vents provided energy gradients and mineral scaffolds, while meteorites delivered pre-made organics like cosmic care packages. Cosmic rays and volcanic lightning acted as molecular blacksmiths, forging complexity through sheer brute force. Clay surfaces and oily slicks offered order amid the chaos, and geothermal cycles refined chemistry through patient repetition. Even Earth's magnetic field might have whispered direction to the earliest molecules, steering them toward the delicate configurations that made life possible. What's astonishing isn't just the diversity of these ideas, it's how many of them might be true simultaneously. The universe rarely works in straight lines. Perhaps life emerged not from a single eureka moment, but from a symphony of processes, each contributing its own verse. The vents built the first metabolic engines, while comets sprinkled the stage with genetic ingredients. Tidal pools concentrated the mixture, and UV radiation sculpted it. No single theory claims the prize because the prize itself might be collective, a mosaic of chemistry, geology, and sheer cosmic luck. As we stand on the brink of new discoveries, with missions drilling into Mars' crust, probes diving through Enceladus plumes, and telescopes analyzing exoplanet atmospheres, the question isn't just which theory is correct, but how many. Will we find icy moons where radiolysis powers subterranean chemistry, or desert planets where UV-baked clays still cradle the echoes of ancient reactions? The answers could rewrite not just our origin story, but our place in the cosmos. So which of these 30 ideas resonates with you? Is it the elegance of the RNA world, the violence of impact synthesis, or the quiet patience of hydrothermal vents? Share your favorite in the comments, because the search for life's origins isn't just a scientific quest. It's a conversation stretching back to the first atoms that dared to bond, and forward to the moment we finally pieced together the universe's oldest recipe.